welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. When was the last time you stopped to appreciate our sun? You know, the star that's been doing its thing for nearly 4.5 billion years. In this episode, we hope to give you a new perspective or expand your knowledge about our star named Sol. We will cover key moments and breakthroughs in the history of solar physics. Then, my guest and I will transition into a Solar Physics 101 to give you the rundown on sunspots, solar flares, the solar cycle, and much more. And then we will wrap things up by discussing how these solar phenomena affect our lives, my guest's exciting research in this topic, and his new book. So, speaking of my guest star, allow me to introduce Dr. Ryan French. Ryan is an astrophysicist researching the sun at the National Solar Observatory in Boulder, Colorado. In particular, Ryan researches explosive phenomena in our sun's atmospheres called solar flares by using data collected from telescopes on the ground and in space. In addition to his work as a researcher, Ryan is an avid science communicator through interviews in the media, social media, and through his new book, as I said, The Sun, Beginner's Guide to Our Local Star. So, now that you've been introduced to my guest star, Ryan, and the topic of this podcast, we're going to head into our first segment where we plan to talk about the history of solar science and the effect that the sun has on our culture. Enjoy.
Sorry, are you anonymous on this? Can I call you Sam?
Oh, yeah, you can call me Sam.
Yeah,
No, you're
Sam.
good. I was going to start out actually by asking you if you prefer Dr. French or Ryan. But I'm not going to do that. Can we just call you Ryan?
Yeah, Ryan is good.
Got it.
But
Okay.
we can include that in the recording if you want. That's kind of funny.
Okay. Gotcha. Okay. Ryan, welcome to the podcast. How are you doing, man?
Yeah, thanks, Sam. Happy to be here.
How's the weather out there in Boulder?
It is pretty hot. I've been in the UK last couple of weeks, so back here in Colorado, it's 30 Celsius. Not sure what that is in Fahrenheit. So a lot of people in the US will tell me that's not very hot, but for me, that feels very hot.
That's a little under what, 90 degrees? I
Yeah,
think?
yeah, sounds about right.
Yeah, 90 degrees Fahrenheit, excuse me. So I don't want to get I don't want to get bullied by anybody that's just using the imperial system.
Objectively, the worst way to measure temperature, right?
Oh. Yeah,
we're starting off controversial today.
Yeah, we definitely made some enemies in the first minute, but oh well. So this first segment, we're focusing on the history of solar physics. But before we kind of dive into the history, I kind of want to start out with the question of where will you be on April 8th, 2024? Just curious.
Yeah, so April 8th, 2024. If the listeners don't know what is happening on that day, you should stick this in your calendars immediately. There is a total solar eclipse. So a total solar eclipse is when the moon passes and blocks out the sun, and that is visible for, I think, millions of Americans this April. So the path sort of starts off down in Mexico, comes up through Texas, through Dallas, San Antonio, up through Cleveland, up to Rochester, upstate New York, into Canada. Anyone along that line will see the sun fully blocked by the moon, allowing you to see with just the human eyes the corona and the extended atmosphere of the sun, which something is normally you can't see this, right? This is the only time. And even if you don't care about astronomy, and I suppose the listeners probably do, otherwise they wouldn't be listening to us chat right now. But even if you don't care about the sun, don't care about astronomy, if you care about just inherently beautiful things, you should make your way to that line, to that path of totality, and see the eclipse. Everywhere else in the US will see a partial solar eclipse, at least in the sort of mainland USA. But if you are able to get to that path of 100% eclipse, you should definitely do that.
Yeah, and maybe I might be miscommunicating this a touch, and you can kind of correct me if I'm wrong here, but the total solar eclipse was one of the ways that we first experimentally proved general relativity, I'm pretty sure. Is that right?
Yep,
we looked at the effect of lensing. Yeah.
Yep.
Look at that.
So this is way back. I'm going to forget the exact year, around 1920. There was
Yeah.
a team of British scientists actually went on an expedition to measure an eclipse, to observe an eclipse. And they found that stars right near the very edge of the sun, their position had been distorted by the sun, and they could measure this during the eclipse. So you're absolutely right. Einstein's theory of general relativity was proven during a total solar eclipse.
Look at that. Look at
Yeah.
that. I didn't even know. See, I'm not even the astrophysicist here, and I'm contributing to the history.
Of course.
Look at that.
And to answer your question, which I just realized I forgot to answer beforehand, Texas is where I will be in April.
Oh.
April
So what
24th.
makes that the most? Is that just like a very advantageous place to be, or what? What's your motive for Texas?
So, to sum up in a short sentence, April in upstate New York is where you don't want to be during a total solar eclipse.
That's fair.
If you look at the weather statistics, because if there are clouds, you're not getting the same experience basically. So if you look at the weather experience everywhere in the US, Texas has got the best odds. I think like a 70% chance of success versus Rochester, New York, which has a 70% chance of clouds, basically. So that's where I'll be. Yeah.
That's fair. Okay, so we obviously just brought up the total solar eclipse that proved general relativity, and I think general relativity, the postulate came out in 1915. I'm pretty sure all of his field equations were posted at that time, and then a few years later it was proven in that manner. So run me through some timelines and some history here. What is the history of eclipses?
So eclipses have obviously been observed for as long as there have been eclipses, which has been as long as there's been people, right? So we've always seen these things. Significant ones through history, there are a few. So this general relativity eclipse was 1919. I just checked and verified that. So that was the big one where they prove relativity. There was an eclipse back in 1860 where they actually unknowingly observed a coronal mass ejection, which is a mass of plasma traveling from the sun. They unknowingly observed that in an eclipse. If you look up diagrams of that 1860 eclipse, you can see there's a coronal mass ejection. It's slow moving, so they wouldn't have seen the motion, but they saw it sat there. And the reason that's quite funny, actually, is because we didn't prove that coronal mass ejections existed until like the 1970s, when we could send satellites into space and measure these things directly. But observations were there from 100 years ago, and we had no idea, which is pretty funny to think about.
No way.
And even today, modern eclipses, the 2017 eclipse, 2019 eclipse, next year's eclipse, we're doing science experiments to further our understanding of the upper atmosphere of the Earth, the atmosphere of the sun, and do a lot of experiments that otherwise can't be done outside of eclipses. So there's a long history of scientists using these eclipses to learn things about, ourselves and the wider universe too.
Yeah, that makes a lot of sense. So just curious, jumping back there, what did they think that was whenever they observed it in the 1800s, the coronal mass ejections?
Yeah, good question. To my understanding, they didn't draw much conclusion from it, or even pay that much attention to what they had seen. So during a total solar eclipse, you see these lovely, what we call streamers, these strips sort of expanding radially away from the sun. And in this one, they had drawn them, but in the sort of the bottom right corner, they had drawn this big sort of circular tangled thing as it was traveling away from the sun. What do they think it was? I don't know. I think the people who were drawing eclipses weren't necessarily the same people who were the scientists answering questions about the sun. So I think there was a bit of a discontinuity there.
Oh, interesting. Something that was kind of just lost in time for a little while.
Yeah.
Interesting. I don't mean to switch gears a little too much here, but from a common person, right? Someone who's not studying astrophysics, the sun is absolutely captivating. Now, obviously, again, I don't condone that you go outside and look at it in the naked eye, unless it's on the horizon, sunset, sunrise. But it's absolutely captivating. So, how has the sun influenced our culture? Could you go through that a little bit?
Yeah, I'm glad you agree that the sun is interesting. One of the most important messages I'm trying to get across is the sun is cool. The sun does stuff. It's not just there, right? But even before we knew how dynamic the sun is, even before we knew about flares, eruptions, as you say, the sun has always been a key part of human culture. Like back in, I don't know, the dawn of civilization, when cities and farming and agriculture first started forming thousands of years ago, these cultures would have immediately recognized, right, that the sun, if the sun's too hot, their crops die. They die. If the sun disappears for too long, again, the crops die. So they put this sort of, I don't know, they put the sun on this pedestal as being the thing that causes things to go wrong or things to go well, even if in most of those cases it's not the sun at all. It's sort of the Earth's atmosphere and the tilt of the Earth and all of these things. So we all know, I don't know, ancient Egyptian culture, ancient Greek culture we learn about in school, right? These cultures, these civilizations, they saw the sun as a god, as like a deity. Like Ra is the Egyptian god, Helios and Apollo are the Greek gods. Funnily enough, bit of a side track. Apollo is the ancient Greek god of the sun. So it's always a mystery to me why the missions to the moon in the 60s were called the Apollo missions. And Apollo is the god of the sun, not the god of the moon. But
Yeah,
anyway,
yeah, that's true. That's
the new
weird.
Artemis missions are fixing that, because Artemis, which is NASA's next round of missions to the moon, is the god of the moon in ancient Greek culture. So yeah, and in a way, these Greeks, these Egyptians, all these other countless societies who worship the god in some way, these were sort of the first solar astrophysicists, right? They were trying to explain the behavior of the sun using the knowledge that was available to them at the time, which was not much. And in a way, that's what I do today. That's what astrophysicists and anyone doing science does. It's just explaining things or proving things using just what is available to them in terms of data.
I'm curious about this since we are talking about history, and this was kind of one of the questions or one of the things that I wanted to address in this podcast, and I think this is actually a really good segue. So at some point there had to have been some hypotheses floating around or guesses, what have you, colloquially or scientifically, thinking about how the sun is even there. Why is it there? What's going on? What's making the sun so bright? And all this sort of jazz. So was there ever like can you run me through some maybe like key transition points of maybe when people stopped thinking like, hey, this is a burning ball of fire in the sky, to actually it's not. It's something, it's a product of nuclear fusion. Do you want to run me through that progression, that timeline?
Sure. So it's certainly incremental, right? This didn't all happen at once.
Yeah, of course.
In Western culture, right? Christianity, for example, the sun was created on the first day, like God, or was it the first day? The sun was created on one of the first days, and up until the 1500s, it was believed in Western European culture that the sun rotated or orbited around the Earth. The Earth was the center of the universe. The sun and the moon orbited the Earth, and the heavens were sort of perfect in these circular orbits. And so the first guy to sort of start suggesting otherwise, there's a few key players, right? There was Nicholas Copernicus, who was the first person to suggest seriously that the Earth orbited around the sun and not the other way around. And he got in trouble for these views. He was prosecuted quite heavily for these opinions. Galileo Galilei, who was the first person to point the telescope towards the sky. He's often credited with being the first person to invent the telescope. That's debatable, but certainly the first person to use it to research space. At the end of his life, he spent on house arrest under guard for suggesting these heretical views that the sun wasn't, or the Earth wasn't the center of the solar system. So certainly incremental, right? Back in the 1600s, this is the first time, again, with the invention of the telescope, that we observed sunspots on the sun. And we discovered the sun is not just constant and unchanging. The sun has structure. The sun evolves. The sun does stuff, right? So it was a long process. We didn't really know for sure what powered the sun via nuclear fusion until much later. That was around the 1900s that we proved the sun is powered by nuclear fusion. That prediction was made, that the sun was made or powered by nuclear fusion, and a key observable of that was that we would detect these particles called neutrinos, and these neutrinos should be around us, produced by as a byproduct of this nuclear fusion process. and they spent decades building these massive detectors underground that could detect these very weakly interacting neutrino particles. And eventually they found the neutrino flux, or the amount of neutrinos necessary to match this prediction. So that's key science there. That's raw science. You make an explanation that sort of explains what you're seeing. So they knew the brightness of the sun, they knew the the size of the sun, all of these things. They make this prediction that the sun is powered by the nuclear fusion of hydrogen into helium. And then you try to then find proof of this prediction. And the best way to do that is to make predictions, very specific predictions, the more specific, the better. And then when you find this, that really, really solidifies that what you're seeing is what you thought that you had seen.
Yeah, and if you didn't get this out of that, which I hope you did, is that the sun is not on fire.
The sun is not on fire.
It's not a chemical reaction, combustion.
Very, very common question, is how can the sun be, quote unquote, burning if there's no oxygen in space, right? And as you say, the sun is not on fire. It's not combusting in the way that we would consider burning here. The word burning is sometimes used as sort of hydrogen burning, but that doesn't mean the same thing. The sun is powered by a physical process, and that is nuclear reaction of hydrogen into helium, which releases a lot of energy in the meantime.
It's a beautiful sequence of both strong and weak nuclear force as well as electromagnetism. It's a lovely dance between those three fundamental forces. And then of course you have to gravity is also a big player in that, or the warping of space-time. We'll just call it.
Yeah, I mean all stars are really is a balance of forces. So you have the gravity of a star trying to pull it downwards, and you need something to resist that collapse of that star. Otherwise the star is going to collapse into a black hole. And in the case of most stars, like the sun, what we call main sequence stars, that is nuclear fusion, which is providing that outward force to resist that gravity. So stars are just a balance of forces. That's all they are.
Yeah. Let's cover a couple more very common misconceptions, and then we'll jump into segment 2 or go into break, and then we'll come back into segment 2. So 2 other things that I think would be fun to talk about is, what is the true color of the sun? So do you want to take us through a little science 101 lesson there? Solar science?
So color, right, is sort of almost a human concept or a human word for different wavelengths. So light can have many different wavelengths. In visible light, the light that we see, red has a longer wavelength than blue, which is a shorter wavelength. So that change in wavelength is just what we would describe as color, right? Humans are limited to just seeing a very small fraction of light. Beyond red, light is in infrared, microwaves, radio waves, and these are just light. It's the same thing, just at different wavelengths, longer than what the human eye can perceive. And wavelengths shorter than blue, you have ultraviolet light, you have X-rays, you have gamma rays. So the sun emits light pretty much across the full spectrum of light. The exception being gamma rays, only produced in very large solar flares, which are these very explosive events on the surface of the sun. But at every other wavelength of light, if you point a camera or a detector sensitive to that wavelength, you will see something. And this is sort of a crucial thing about solar physics, is different parts of the sun's atmosphere, different parts of the sun's surface emit light at different wavelengths. But if you're just including like the bulk color, what is the main color of the sun, just to answer your question, right? The basic answer is white. The sun emits red light, sun emits orange, yellow, green, blue, indigo, violet, emits that whole wavelength of light, which to the human eye is perceived as white. And when that sunlight passes through raindrops, that white light from the sun, it's split up into that colored spectrum, right? The rainbow. So those colors you see in a rainbow, they come from sunlight. So that's sort of the basic answer. And if the human eye was sensitive to a different range of wavelengths, we would see it at a different range of wavelengths, right? But if you're talking about sort of the peak wavelength, where is the brightest wavelength that the sun emits? It's actually sort of green in color. So the brightest wavelength of the sun is sort of green, but it's not really useful to say the sun is green, because it's not, because the sun emits, as I said, the entire range of visible light, and those colors mix to make white, even if green is slightly brighter than yellow or blue or red. It doesn't overwhelm it to the point that we see the sun as green.
It makes sense.
What the sun is not is yellow. The yellow sun, as we were discussing beforehand, which is the color that you would draw the sun at school, is actually an atmospheric effect of Earth and not due to the sun itself.
Right.
If the sun is low on the horizon, then the sun is red. Right? And the reason that we see the sun as red during sunrise and sunset is because the shorter wavelengths of light as they pass through the atmosphere are scattered, and we lose that, and just the red light reaches our eye. If you're somewhere where there's wildfire smokes or dust in the air or even pollution, then that slowly starts to scatter out the lower wavelengths of light, and it sort of shifts the tone of the sun. So if you live somewhere, as I said, smoke, pollution, dust, whatever, the sun will be more yellow. So some people have asked me, why was the sun yellow when I was a kid and now the sun looks white? The simple answer for that is you probably lived somewhere where there was worse air pollution when you were a kid than there was now. Maybe you live somewhere where there used to be a lot of manufacturing, and that manufacturing has gone, and now the air quality is better. So it is true that sometimes we see the sun as yellow through the atmosphere, depending on how thick the atmosphere is. But most of the time, it's white in very clean air, and above the atmosphere, the sun is white all day long.
Yeah. I think from like a quantitative perspective, and this is like really brute, of course, because I'm sure you could definitely correct me in a way more sciencey manner. But like if the sun was above you, you think about it as a 1 atmospheric thickness. And that scattering effect that you were talking about, is it the Rayleigh or Rayleigh? I don't remember.
Rayleigh scattering, yeah.
Rayleigh scattering,
sort of the blue sky.
And then when it's on the horizon, I've heard anywhere, if you use simple math, it's like 8 to 10. I think more towards 10 times the atmospheric thickness that light has to go through. So that's why it's much more scattered, and that's why it appears more yellow, orangish red.
Yeah,
on the horizon.
Certainly. And even if the sun is directly above you, if you just increase the air thickness from smoke or dust or sand, then changes the color. In the UK, we sometimes have like dust storms from the Sahara, sandstorms that sort of get high in the atmosphere, and that can change the color of the sun. Here in the US, Colorado, where I am right now, the same thing can happen with wildfire smoke, right? There's a bunch of things that can do it.
Very true. Very true. Okay, so the last thing I want to talk about, just for funsies, is we're actually not seeing the sun in its present state whenever we view it. Correct? Yes. Why is that?
Yeah, so light, right, which is what you're seeing coming from the sun, travels at a finite speed. So that speed is 300,000 kilometers per second in a vacuum. It's slightly shorter than that if it goes through air or water, things like that. And because the sun is not, right on top of us, that sunlight takes time to travel. So essentially, by the time the sun reaches your eye, that actually left the sun 8 minutes or 8 and a bit minutes ago. So essentially, you're seeing the sun a little bit back in time. And the further back you look, so if you look at, the further away you look, so if you look at stars, if you look at galaxies, you're actually seeing progressively further and further back in time. And this is crucial because if you look far enough, then you can see, the very early formation of galaxies. You can even see the point at which the universe became opaque. And this happened way back a little while after the Big Bang. So we can see that, and that's called the cosmic microwave background. And you can see the formation of everything happening around you. So when you get people saying the universe is not X billion years old, it's not expanding, it's a bit of a joke because you can literally see that as you look further away.
Literally in every direction that you can too.
Every direction. It's all the same.
Yeah, because key point, the Big Bang happened everywhere, not just from like a finite point in the sky. So that's pretty cool. So I think with that, we're going to jump into our first commercial break, and then when we come back, we're going to like dial it up a notch and talk more in depth about the solar cycle and some sunspots and solar flares and coronal mass ejections. So stick around. All right, we're back. This is segment 2, and this is the continuation of what we kind of started in segment 1, calling it solar physics or solar science 101. And in this segment, it's going to be a little more in depth. We're going to talk about, I guess, let's start out here. let's pose the question first, or
Mhm.
pose the situation, because this year is extremely extraordinary for the fact that we're not only feeling, I'm sorry, anthropogenic climate change, we're also feeling the effects of El Nino, and on top of that, we're also dealing with the height of the solar cycle. So tell me what do we mean by the height of the solar cycle? What is that?
Sure. So the sun is not constant in the amount of stuff that it does. So on the sun, we have sunspots, which are sort of dark, dense regions of the sun's surface. We have solar flares, we have eruptions, and these follow what sort of described as a solar cycle, or a cycle of increasing and decreasing activity on the sun. So this cycle is around 11 years long. And at the bottom of this cycle, which we call solar minimum, the sun basically does very little in its atmosphere. There are no sunspots, there are no flares, there are no eruptions. Now, at the peak of that solar cycle, we can have hundreds of sunspots on the sun at the same time, hundreds of solar flares, hundreds of eruptions every month or even every week on the sun. So we're currently ramping up in a period of increasing solar activity. I think December 2019 was solar minimum, was the lowest that the sun's activity got in this recent cycle. And so we're currently ramping up. So somewhere between 2024 and 2026 will be at the maximum, or the solar maximum, of this local period of solar activity.
Interesting. So, and this is just maybe a question that maybe like the audience member might have. And what is sparking this maybe not extreme, but like from the layperson, it feels like this 11-year difference is extreme. But what is causing it? Like, why on some years we have much more sunspots than in other years?
Yeah, so in the atmosphere of the sun, unlike the core of the sun, which we were talking about previously, which is dominated by nuclear fusion, the atmosphere of the sun is essentially all dominated by electromagnetism. So magnetic fields and electric fields as well. Magnetic fields are why we get sunspots. Magnetic fields are why we get flares. It's a conversion of magnetic energy that's in the atmosphere of the sun that's converted to light, acceleration of particles, heating. That's what a solar flare is. As to why we get this 11-year cycle, let's start off by saying that at solar minimum, the sun's magnetic field is very basic. It has a north pole, has a south pole, and that sort of makes you can picture sort of a dipole similar to what the Earth's magnetic field looks like. But the sun, unlike the Earth, is not rigid. Different latitudes, different parts of its surface rotate at different rates. So the equator of the sun rotates every 24 days or so. The poles of the sun rotate every 30 days or so. So what this does is the sun it's a very simple magnetic field, starts to wind up because the equator of the sun is rotating faster. So it begins to wind up. And as you wind up this magnetic field, it becomes a lot more concentrated, a lot more complex, starts interacting and interfering with itself. And where these sort of periods of complex magnetic structures sort of reach the surface of the sun, that is where we have sunspots and eruptions and coronal mass ejections, all these fun things. And as the sun continues to rotate and coil up, eventually these complex regions all are pulled below the surface of the sun, and then you're left with a very simple magnetic field, sort of with what you started with. And that cycle takes about 11 years, and that's why we have these periods of very high activity and very low activity, depending on what the global structure of the sun's magnetic field is doing. As to why it's 11 years specifically, and not 100 years and not 11 days, we don't know. And we also don't know why not all solar cycles are the same. Some solar cycles have a very large maximum, some have a very low maximum. So even between this minimum to maximum cycle, sometimes the sun is a lot busier than others.
When we peer towards the sun, right, we're also seeing similar behaviors in maybe nearby stars that we can observe. Is this?
Certainly, yeah. So solar flares happen on the sun. And we know a lot about solar flares because we can resolve the sun with great spatial resolution and great time resolution as well, with a lot of different wavelengths. But in other stars, we see them too. We can't resolve them spatially. We can't see a brightening, in a disk, like in a circle, like we do on the sun. But we can see in different wavelengths of light, other stars have flares too. We call these stellar flares. Some stars have flares that are 100,000 times brighter than the solar flares we have on our sun.
Nice. So you talked about the surface and then the core, I guess the sun's atmosphere. But my understanding, it's kind of broken down into more of a layer cake. Do you want to run through the layers just to give people some cool trivia knowledge?
Sure, sure. So we have the core of the sun, okay,
Mhm.
and then coming out from the core of the sun, which is where all the energy is released, we have what's called like, again, we're inside the sun at the moment, called the radiative layer, which is where heat and energy is transported via radiation. And
Mhm.
then the next layer that sort of reaches to the surface of the sun is called the convective layer. So we have convection, like if you boil water in a pot, you have bubbles of water coming to the surface. We have that on the sun as well, and you can see that with telescopes. And that brings you to the photosphere. The photosphere, as it's called, is essentially the surface of the sun. This is the layer that produces the light that we see with white light. But then above the photosphere, it keeps going. We have a layer called the chromosphere, which is a bit cooler, a bit colder than the surface of the sun. Densities are beginning to fall here. But then above
Mhm.
the chromosphere, you get the atmosphere of the sun, where things are hotter, again, actually hotter than the surface of the sun. But the densities are really, really low. This is really essentially, if this existed just above the Earth, you would essentially call it a vacuum. The densities are so low, but we can see these bright features in ultraviolet light, and this is where we see flares and eruptions up in this less dense but hotter region, which we call the sun's atmosphere or the corona.
So why is there a lesser density, but yet the heat is greater? Why is that?
Yeah, so the density is falling off because you're leaving the sun, essentially, right?
Hmm.
So the atmosphere of the sun, the further you get, the less dense it is because gravity pulls things closer to the sun in general. Same on the Earth. The reason it's hotter, this is an ongoing puzzle in solar astrophysics. It's called the coronal heating problem.
Oh,
Often when the coronal heating problem is discussed, it's sort of misposed
oh,
because the problem isn't where does the heat come from, because the heat comes from the sun's surface. Although temperatures are higher, because density is a lot less in the atmosphere, the energy density, or like the total energy, is a lot less than the surface, even though the surface has like a colder temperature, if that makes sense.
hmm,
So the problem isn't where the energy comes from, where the heat comes from. It's how does the energy get from the surface of the sun to the atmosphere. So it's not a coronal heating problem. It's almost like a coronal heat transport problem. But the two
ah,
main theories, both these theories work in theory, and in reality, it's probably a combination of these. But we don't have observational evidence yet to prove either one. But the two main models, one is the nanoflare model. So the idea that the same thing that causes solar flares is happening on scales a million times smaller than solar flares, but happening everywhere all the time. And so over sort of integrated over the entire sun is releasing enough energy to heat up the sun's atmosphere. The
okay.
second is called the wave heating model, where your magnetic fields, which stretch through the atmosphere of the sun, are basically vibrating in a way that we can't yet observe with the instrumentation that we have. And these vibrations are again transporting heat and energy to the atmosphere of the sun. But in both cases, basically energy is coming from the magnetic field into the heating of the plasma.
Ah, I see. So, I know you said yet we don't have anything yet that can measure these things. Is there efforts to create some sort of ground base or maybe spatial telescopes to check this out, or is there any missions that are going to be sent? What's going on there?
So there are a lot of missions to study the sun. We're really fortunate. It's important to study the sun for lots of reasons, one of which is, the sun can influence our technology here on Earth.
Of
So
course.
there's a lot of money that goes into trying to understand how the sun works. When I say there hasn't been observational evidence, there hasn't been conclusive observational evidence. So we have instruments at the moment from a bunch of different spacecraft, from NASA, European Space Agency, Japanese Space Agency,
Hmm.
even now the Chinese Space Agency and the Indian Space Agency just last week launched another mission to research the
Right.
sun, which is really cool, called
Yeah.
Aditya. So certainly there's evidence to support both of these models, but we haven't found that sort of conclusive smoking gun just yet. But we have a lot
Understood.
of missions coming up. There's a big telescope in Hawaii built by the National Science Foundation's National Solar Observatory. That's called the Anoye Solar Telescope, a massive 4-meter diameter telescope. We have a NASA mission coming out called MUSE, which is the multi-slit explorer, which is launching 2026 or 2027. A Japanese mission coming in 2027 as well, called Solar C. There's a bunch of new exciting things coming up, which hopefully will shed more light on not just the coronal heating problem, but other open puzzles in sun science as well.
Yeah, that sounds amazing. That's a great lineup. It's a good time to get into solar physics.
Yeah, they're calling it the golden age of solar physics. So with NASA's Parker Solar Probe and European Space Agency's Solar Orbiter, which are already orbiting the sun, we're not just getting views of the sun from different wavelengths, but also different positions around the sun as well. So you're getting sort of multi-angle views of these things.
See, Elon, you don't have to just take something and ram it into the sun to prove yourself. You can actually be beneficial to actual science.
I think he's not a big fan of the sun. I think back in January, February, either this year or last year, I can't even remember now. There was a large flare that expanded the upper atmosphere of the Earth, which happens every time we have a flare. But it happened during a launch of his Starlink satellites. So he had 60 Starlink satellites that didn't make it to the atmosphere. They deorbited and crashed basically because of a solar flare that happened mid-launch. So I think the sun is not in his good books.
Wow, I did not know that. That's interesting. So yeah, I'm glad you kind of prefaced that because the sun does have wreak havoc on our technology from time to time. Maybe it'd be fun to talk about this is the Carrington event? Isn't that like
event.
Okay, yeah. Would you want to take the audience through the Carrington event?
Sure. So the Carrington event is essentially a very big solar flare way back in 1859. It's called the Carrington event after a man called Richard Carrington, who was the first guy essentially to link a flare on the sun to stuff happening at Earth. He was observing the sun one day. His job actually was only a part-time astronomer and a part-time brewery owner. So a great job combination. But he was observing the sun. He saw this white feature on the sun that was sort of moving over this sunspot, so fairly sort of zoomed in. And that night, the aurora was seen basically all over the world, all the way down to south of Florida, the Caribbean, south of China, Japan, northern Australia, places that had never seen the aurora, at least in recent history, saw the northern lights. And over in Europe, which sort of in daytime at the time, this eruption reached the Earth. Telegraph machines, which was the peak of technology at the time, they were giving electric shocks to operators. They were sending and receiving messages, even with no electricity connected. And it was a whole weird thing that nobody really knew what was going on. But Carrington was the first person to observe this. And what had happened is this massive solar flare had triggered an eruption, which we call a coronal mass ejection. So a ejection of mass from the sun's atmosphere, the corona. And this took about 12 hours to reach the Earth. And as it did, it interfered with the Earth's magnetic field, which essentially, if you change the magnetic field of something, you can create an electrical current. Mm-hmm. So this electrical current was sending and receiving signals through these telegraph machines. It caused the aurora, etc. So this Carrington event is often considered like the worst case scenario for if a similar event had happened today. And again, we don't know with certainty what would happen if that same event happened today because we haven't had one that big. But current estimates are about 1 in 5 satellites might stop working.
Wow.
That's sort of the biggest financial hit is that.
Wow.
Astronauts in space are potentially at risk from increased doses of radiation.
Yeah.
On the ground, radio waves, which is how we might communicate, right, via radio communication, don't work if you expand the upper atmosphere enough. So if there's a very large flare, your radio communications could go for hours, maybe even a day. So aviation, airlines, shipping, logistics would all be stopped for a couple of days. So very financially disruptive thing. And also on the ground, you might have certain regions, especially ones with older power grids that are more vulnerable and more centralized. You could have power outages as well. So some power grids will be damaged. It won't be a global electric wipeout like it's sometimes pointed as, but you could have some regions where your power grids are significantly damaged and could take weeks to repair them. So it's a fairly big thing, and it's predicted to cost as much as any other natural disaster that we've had on Earth. but with no direct threat to human life on the ground. I think is an important caveat there. So when we try to understand the sun and forecast flares, understand how they work, sort of the end goal for that is to mitigate the impacts of large eruptions from the sun, such as this one in 1859.
Yeah. Was the 1859 Carrington event, was that during the height of the solar cycle, or was this just a random event?
It was certainly towards the peak. I
Oh,
don't know if it
okay.
was exactly on the peak, but it was up there. It might have been on the declining phase of the solar cycle,
Got
but
it.
it was up there, yeah. But it's also
Interesting.
worth noting it doesn't need to be a Carrington-sized event to cause damage. As I mentioned
Right.
before, a flare last year, just a random flare, not even a particularly large one, deorbited 60 Starlink satellites.
Wow.
There are stories like this. 1989, a hydroelectric plant in Canada lost power for half a day. Millions of people without electricity, again, from an eruption from the sun. There are also cases in the Cold War where a solar flare was almost mistook as a Soviet EMP, and
Oh my
you can
goodness.
imagine how that could have gone if things had played out a little differently
Ooh.
there. But thankfully, one guy on board knew what a solar flare was and thought maybe we should check before we launch a preemptive response to what may or may not be an enemy attack.
My goodness.
Yeah,
Wow.
yeah.
From like dialing it back though, does air traffic control do they like have data that comes in, or people like an agency that warns them of these events just in case they have thousands of flights in the air at one time?
They do. They do.
Okay.
There are groups around the world that forecast what we call space weather, which is all this influence from the sun on Earth. So in the United Kingdom, it's the Met Office does this. In the US, it's NOAA, which is like the weather
Oh,
forecast organization. The US military have their own one as well, and I think
mm,
South Africa, Australia have got their own ones. So certainly airlines receive forecasts for these things, so they are aware of it and have procedures and protocols in space.
yeah. Oh, that's cool. I did not know that NOAA was in charge of informing for flights. That's
Yeah, yeah,
and space
it's called
weather.
the so it's NOAA SWPC, which is the Space Weather Prediction Center, and they're sort
Wow.
of probably the global leaders in forecasting space weather.
I am so pro getting NOAA more of a bigger budget. That's my opinion. I think their budget's too small, but we're not talking about. No, that's pretty cool. Is there any other things that you would like to address from the solar physics kind of 101 aspect that we haven't covered quite yet?
Uh, Nothing specific. I just want to drill home the main points. Like, why do we bother learning about the sun at all? Two
Yeah.
reasons. One is space weather, as we discussed, its very
Mhm.
real impacts. And the second, we sort of touched on a bit earlier. The sun is the only star in the sky that you can resolve with any sort of resolution, right? So by learning about the sun, you're learning about not just other stars, you're also learning about how plasma and magnetic fields work in hot
Mhm.
space environments. So it can teach you about exoplanets, about black holes, and can teach you wider, almost universal questions about space that we wouldn't know if we couldn't observe the sun the way we can. So those are sort of the two main reasons why the sun is interesting to me and why it should be interesting to everyone, I believe.
Yeah, yeah, definitely. That's man. I kind of want to ask one more question, just
Yeah,
for
go for it. Go for
funsies.
it.
I'm a big fan of nuclear fusion energy. And
Hmm.
so my whenever you said like in these extreme environments, we want to understand, how magnetic fields behave and things like that.
Sure.
Is the research in solar physics also applicable and being applied to fusion energy? Do you know anything about that, or maybe that's just kind of way
Yeah.
out there in the
So
distance?
to answer your question, I have two ex-colleagues who did
Ooh,
their PhDs in sort of solar wind plasma physics, so the physics of stuff coming off the sun, who now work for the UK atomic physics department working on nuclear fusion. So
that's
there are certainly links, yes.
that's pretty cool. And it's also good to just continue to note the fact that there is interdisciplinary work going
Hmm.
out there. Scientists don't just sit in a room and play on or work on their computer and never talk to anybody.
At least they shouldn't do.
Yeah, right,
Even
right.
if some do.
Yeah, that's true. It's not the correct model, but
Yeah.
All right, cool. So I think that concludes our solar science, solar physics 101 course, and then whenever we come back, we're going to talk about Ryan's research and his book. So stick around. Okay, we are back. This is segment 3, the final segment of this episode, and we've been talking about what we know, a little bit about what we don't know about the sun, and we did touch on this a decent amount in segment 2, but I want to kind of go into Ryan's research a little bit more. So
Sure.
Ryan, what are you researching?
Yeah, so as we sort of discussed, there's a bunch of things we don't know about the sun, right? Sort of the 3 main puzzles. We don't understand what drives the sun's dynamo, why the cycle is 11 years, not 100 years. We don't know why the atmosphere of the sun is as hot as it is. And the third is we don't know specifically what triggers and how to forecast eruptive events. So different people work on different aspects of those problems. So just taking the last one as an example, this is sort of how I'm involved with the whole thing. Solar flares. Some people research when a solar flare erupts, how does that eruption evolve between the sun and the Earth? Some people research what happens when that eruption reaches the Earth. How does that change things? Me specifically, I'm trying to understand what happens to cause a solar flare. Why do solar flares happen when they do and not at other times? And what physical processes, what physics is happening when that flare takes place? So I use data from a massive range of telescopes, both in the ground, in space, and essentially I take the theories that come out of the computer simulations and stuff like that, and essentially I'm looking for observational evidence to prove or disprove those theories. So I'm an observationalist, and other people are doing the simulations and the theory side of things. So observational evidence of solar flares, that's my jam.
That's pretty cool. Huh. So now this is just solar flares in general. So it could also be potentially attached to one of the theories that you posed to why there is a temperature difference between the layering of the sun, right?
Yeah, certainly. So flares are just triggered by this release of energy from magnetic fields, and that possibly also happens on very, very small scales as well. So, my interests are fairly broad in terms of dynamics in the atmosphere of the sun. Solar flares, big flares are my favorite, I would say. But I have worked and published work on very small flares and even tiny little brightenings within very cores of sunspots as well.
Oh, interesting. That's pretty cool. So where are you doing your research? What laboratory?
Yeah, so I currently work at a laboratory out in the United States, here in Colorado. It's called the National Solar Observatory, funded by the National Science Foundation. And before that, I was back in the UK finishing my PhD at University College London, UCL.
Nice. That's awesome. So you're definitely liking the transition from the UK to Boulder?
I really like it in Boulder. I like the weather here. I like that in the winter, even if it's cold, it's still sunny and it's not just cloudy and overcast, which the UK is a lot of the time. And I'm a big outdoor guy.
Nice.
I would say back in the UK, I was relatively fit in terms of UK standards, but in terms of Colorado standards, I'm like way below average. So it's an adjustment, certainly.
Not a lot of bangers and mash in Boulder.
Not a lot of bangers and mash. There is actually an English pub down the road that actually do bangers and mash.
Oh yeah, yeah. How is it? Is it okay?
It's fine.
It's fine. It's fine. It's not up to the standards. Is what I'm getting from that.
Your words, not mine.
I guess I'll have to be the judge if I ever go out. But so that's pretty cool. So and I also know that you were heavily busy in the process of publishing and writing your latest book, the Sun's Beginner Guide to Our Local Star. So can you run us through that process? I mean, it seems, I've heard so many people that say, man, I just really want to write a book. I really want to write a book. But, maybe they just aren't familiar with how, strenuous the process may be, or maybe not so strenuous. So take us through, what you had to deal with.
Sure. Yeah. So I was pretty keen to write a book. I'm big into outreach and communicating science, from very complex things to things that are interesting to the general public, right? Hopefully that's what we're attempting to do here as well.
Yeah.
And throughout the themes of some of my science talks, I began to think like, there's a narrative here that I think would translate really well into a book. So approached someone who I knew who was also an author, sort of asked for some contacts and pitched this book and sent all this stuff off. And eventually they decided that they would pay me to write a book, which was fantastic.
Nice.
And as you say, it was a lot of work, not only just writing the text, but I made a lot of graphics from scratch as well. But it was worth it, I think. The book published back in the United Kingdom back in May, and is publishing in mid-September in the US, which may be before that you're listening to this, depending when this comes out. So yeah, currently working on some promotional stuff for the book, especially as it comes out to US markets. And I think people are enjoying it, which is fantastic. You never know when you write this thing, even if your publicists and your editors read over it, you don't know. It could be really, really bad, right? It could be really, really bad. You're not sure, but thankfully it seems to be going okay. And I think it's a nice, fun little guide to why we should care about the sun, fun things the sun does, how we know everything about the sun that we do, and also tips on how you can observe the sun through eclipses and accessing data online and all of that fun stuff.
Yeah, you know what? I'm going to hype it up a little bit, obviously, but and it's not for the case that you're obviously on this podcast, but I did purchase your book. I've been reading it and I've loved it so far. It's been wonderful. It has a fair share of in-depth information, but it also, is very relaxed, and you can, it's not like you need to study the sun for a living to be able to understand it. It's a great guide to just having a great perspective of our star. So it's good. I really like it so far.
That's really kind. That was the goal, something that was accessible to everyone. So I'm really happy to hear that. Thank you.
Yeah, absolutely. And also, by the way, if whoever is watching or listening to this, I'm going to make sure that I throw some links out there. That way, probably in the show notes or what have you on the website and everything that you can go to and go purchase Ryan's book, because this man needs some dough, and he wants to make sure that you understand and you love the sun just as much as he does.
That's the more important point. That's the more important point. We'll go with that
one. But yeah, no, that's really cool. So I know you said that you've been science communicating, but what was the motivation in terms of writing the book? Did you just feel like you would be able to get your information out better in that manner, or what was your motivation?
Yeah, so I sort of started posting on TikTok around the time that I sort of had this idea of doing this book. And it sort of occurred to me that a lot of people don't know that the sun does anything. We see the sky every day, and it's the sun every day in the sky sort of looks relatively constant and unchanging to us. And it's only when you start looking at it with specialized equipment, you see that that's not true. So really, I just wanted to give people an appreciation that, one, the sun does stuff, and secondly, that it's important to understand the stuff that the sun does do for reasons that we've been talking about for the last however long it's been so far. So yeah, that was my goal, that people will get an appreciation of the sun.
Yeah. So is there a specific portion of the book that you really, really love most by chance?
So I really like the first section. I've got a copy sat right here.
Hey, there it is.
I like the first section, which sort of goes through the history of how the sun was observed, why we know everything about the sun that we do, and sort of interesting, semi-entertaining stories of astronomers and what they were doing along the way to try and figure out all this stuff about the sun. That's my favorite bit.
Yeah. No, I actually heavily enjoyed that section. I'm not really a history buff, but that was really, really good to also like reinforce my scientific history, because that you don't get that on an everyday basis. So I definitely enjoyed that portion of the book. That was good.
So a fun little fact from that is, for hundreds of years, astronomers were debating what are sunspots. Right? They saw these things as soon as you point a telescope at it. They knew they were there. They didn't know what they were. And there was an astronomer called William Herschel, who was a very accomplished astronomer, discovered one of the planets in the solar system, really important guy, and he thought, and he pretty accurately predicted that sunspots were colder parts of the surface of the sun. But he said that there's probably life living in the sunspots on the sun. So this guy who was really accomplished discovered a planet, thought there were aliens living on the sun. And I think that just is a good life lesson that, you know, people who are really good at some things get it wrong as well. And if you yourself or whoever's listening, you know, everyone makes mistakes, sometimes catastrophic mistakes. And I think that's okay. That's just part of the process, right?
Cool, man. I think this has been a wonderful podcast. I mean, the people who are watching or listening to this is going to get some pretty cool history facts about this, learning more about the sun and its processes, and maybe just gaining a better perspective on the thing that literally stares us in the face every day when we go outside. So yeah, this has been wonderful. Thanks for being on the podcast, Ryan. I appreciate it.
Thanks for having me, Sam. This has been good fun.
Yeah. All right. Well, cheers. That is all for this episode of Everything STEAM. I just wanted to take a quick second and thank Ryan for sharing his knowledge and expertise with regard to history, solar science, and much more. If you want to see more of Ryan's content or give his fantastic book a read just like I did, feel free to head to my website, everythingsteam.org, and go to this episode's page, or just head on down to this episode's show notes in your respective platform. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont. The clips that you'll see on social media were created by our intern Molly Chakery, and our episode art was created by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. We're always looking for feedback, and the rating would greatly help us out in the fight against those algorithms. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and just fun STEAM content. Just search Everything STEAM on Instagram, TikTok, and Facebook to join in on the fun. Once again, thank you for listening to Everything STEAM. I'm your host, Sam Stanford, and as always, stay curious.